มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้าวิทยาลัยเพื่อการค้นคว้าระดับรากฐานสถาบันสำนักเรียนท่าโพประกาศจัดตั้งขึ้นเมื่อวันที่ 14 มีนาคม พุทธศักราช 2554 รับรองสถานะโดยสภามหาวิทยาลัยนเรศวรให้สถาบันสำนักเรียนท่าโพสำหรับฟิสิกส์ทฤษฎีและจักรวาลวิทยาหรือ TPTP ซึ่งแต่เดิมนั้นดำเนินการภายใต้จิตอาสาของเหล่าคณาจารย์ฟิสิกส์มาสเตอร์ทัพพาเอียนตั้งแต่แรกเริ่มเมื่อวันที่ 8 สิงหาคม พุทธศักราช 2539 ต่อเนื่องยาวนานจนเป็นสถาบันแห่งการผลิตผลงานศึกษาวิจัยและเป็นอาสมบ่มเพาะนิสิตสาขาวิชาฟิสิกส์ทฤษฎีให้มีความรู้ความเข้มแข็งทางวิชาการจนได้รับการยกสถานะให้เป็นหน่วยงานระดับคณะวิชาอย่างเป็นทางการถือเป็นการประกาศเจตนารมณ์ผลักดันยุทธศาสตร์พิเศษของมหาวิทยาลัยนเรศวรที่จะก้าวเป็นมหาวิทยาลัยวิจัยชั้นนำของประเทศในระยะเวลา 10 ปีที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตผลงานต่างๆมากมายผลงานวิจัยตีพิมพ์ระดับนานาชาติจำนวน 125 บทความผลงานวิจัยตีพิมพ์ระดับชาติจำนวน 8 บทความงานประชุมวิชาการระดับนานาชาติจำนวน 7 ครั้งงานประชุมวิชาการระดับชาติจำนวน 10 ครั้งการจัดอบรมเชิงวิชาการระยะสั้นและโครงการบริการวิชาการจำนวน 58 โครงการการจัดสัมมนาวิชาการ 200 ครั้งคณาจารย์ของวิทยาลัยได้รับรางวัลเชิดชูเกียรติทางวิชาการจำนวน 15 รางวัลบันทึกข้อตกลงความร่วมมือกับสถาบันชั้นนำอื่นๆจำนวน 13 สถาบันหนังสือและตำราวิชาการจำนวน 13 เล่มวิดีโอสอนออนไลน์ผ่าน EVE Channel จำนวน 34 วิดีโอนอกจากนี้ SIP Plus Consortium ได้สร้างเครือข่ายความร่วมมือทางวิชาการระหว่างสถาบันฟิสิกส์กว่า 20 สถาบันกลุ่มเครือข่ายพิษณุโลกฟิสิกส์เน็ตเวิร์กได้ส่งเสริมกิจกรรมสัมมนาวิชาการในจังหวัดพิษณุโลกและสถานีฟิสิกส์ศึกษาคือการให้ความสำคัญกับครูผู้สอนฟิสิกส์ในโรงเรียนระดับมัธยมศึกษาให้เข้มแข็งและถ่ายทอดสู่นักเรียนผู้เป็นอนาคตของประเทศที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตบัณฑิตสำเร็จการศึกษาในหลักสูตรวิทยาศาสตร์มหาบัณฑิตจำนวน 8 คนหลักสูตรประกาศนียบัตรบัณฑิตชั้นสูงจำนวน 10 คนหลักสูตรปรัชญาดุษฎีบัณฑิตจำนวน 5 คนผลงานเหล่านี้จะสำเร็จขึ้นมาไม่ได้หากปราศจากผู้สนับสนุนและแหล่งทุนวิจัยอาทิมหาวิทยาลัยนเรศวรสำนักงานกองทุนสนับสนุนการวิจัยสกว.สำนักงานการวิจัยแห่งชาติวช.ก โครงการปริญญาเอกกาญจนาภิเษก คปก.นิวตันฟันด์ศูนย์ความเป็นเลิศด้านฟิสิกส์เทพสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมูลนิธิโทเรเพื่อการส่งเสริมวิทยาศาสตร์ The Abdus Salam International Center for Theoretical Physics ICTP อื่นๆปัจจุบันวิทยาลัยเพื่อการค้นคว้าระดับรากฐานมีคณาจารย์ทั้งหมด 9 ท่านโดยแบ่งเป็นคณะผู้บริหารวิทยาลัย 4 ท่าน 3 ห้องปฏิบัติการวิจัยห้องปฏิบัติการวิจัยจักรวาลวิทยาและความโน้มถ่วงห้องปฏิบัติการวิจัยทฤษฎีสนามควอนตัมและฟิสิกส์พลังงานสูงหน่วยวิจัยฟิสิกส์ดาราศาสตร์และจักรวาลวิทยาเชิงคำนวณจากอดีตถึงปัจจุบันเรายังคงดำเนินการภายใต้พันธกิจสำคัญอย่างต่อเนื่องดังประกาศเจตนารมณ์ท่าโพณวันที่ 8 สิงหาคม พุทธศักราช 2539 เราจะสร้างโรงเรียนฟิสิกส์ที่ดีที่สุดแห่งหนึ่งของประเทศขึ้นที่นี่ โดยหวังเป็นอย่างยิ่งที่จะส่งเสริมสังคมแห่งการเรียนรู้จุดประกายเยาวชนและสร้างบุคลากรให้มีความเข้าใจลึกซึ้งเห็นถึงความสำคัญของวิทยาศาสตร์พื้นฐานต่อยอดวิทยาการความรู้ด้านต่างๆให้ก้าวหน้าบนรากฐานที่มั่นคงทางวิทยาศาสตร์ซึ่งเป็นกลไกสำคัญให้ประเทศไทยขับเคลื่อนไปอยู่ในระดับแนวหน้าของโลกในอนาคต
Okay, good afternoon, everyone, and welcome to ETH Colloquium online seminar, series number 8, organized by the Institute for Fundamental Study, National University, Thailand. And my name is Kalin Yukong. I am ETH Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Let me first give you the idea why we need to do this kind of activity. Most of the time, academic conversation would normally circulate among scientists, yet it's bridging the gap between the science world and the general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and enjoy in progress of the advanced research. For this talk, we are very pleased to have Dr. Napat Poovuttikul from Department of Mathematical Science, Durham University, United Kingdom, to talk on the topic duality, how the ADS universe is a hologram. Let me spend a little bit more time to introduce our speaker formally. Dr. Napat completed his bachelor degree in physics from Imperial College London, United Kingdom, and his master degree in quantum field theory and fundamental forces, again from Imperial College London, United Kingdom. Then he completed his Ph.D. in theoretical physics at Lowland Institute for Theoretical Physics, Leiden University, Netherlands. Currently, he's working as a postdoc at Department of Mathematical Science, Durham University, United Kingdom. His research area are in the wide range from, I believe, quantum field theory to graphene and electronic fluid. Well, correct me if I'm wrong. The talk will be lovely, 40 minutes long, I believe. Before I stop doing the talk, if you have questions, you can put them in the comments. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this screen to our speaker, Dr. Napat. Please. Yeah. You need to turn on your microphone, I think.
Okay, thank you. Let me try to share the screen like as we practiced before.
Yes. I think I can see your screen now.
I think that is the slide which I think you should
have.
removed.
All right. Okay.
So this one, this would work.
Okay.
Okay, let's see. It's moving up and down, I suppose.
Yes.
Okay, amazing.
Okay.
All right. Okay, so thank you the organizer for this opportunity for discussions. And let me say a few words before the talk. So first of all, this is not an advertisement for my work. It's rather an overall view of the research that I've been working on. And this is so that we can actually have a meaningful conversation either with the organizers or the audience who will be hopefully will ask a lot of questions afterwards. Most of the results here are roughly 20 years old or more. But despite the age, it is still a very active area of research. And by active, I mean there are many open questions, so that I cannot, by nature of it, I cannot answer everything. And so consequently, I should say some disclaimer that this is my view, like my personal view on the topics, which many would agree, but also like they are more liberal point of view on the subject. Also, I assume that the audience would know some basic physics like electromagnetism or Lagrangian, roughly around undergrad level. If you don't, then I guess this talk might not be for you. I mean, you can try, but like there's so much I can prepare for 40 minutes. So with that out of the way, let me discuss the title with the duality and how the ADS universe is a hologram, with emphasis on how. So I think before we say anything, it's important to understand the framework in which we agree upon whether things are true or not before asking how or why. Because otherwise you're gonna perpetually ask how and why repeatedly. I think this statement is kind of self-explanatory, but if you want to adhere to the authority, then you can watch this video, which I hope will be uploaded. The slide will be uploaded soon, of Richard Feynman, when he was asked to explain how the magnets feel each other, and like the conclusion is that it's not really possible to explain before we agreeing about the concept of fields and the tools that we use beyond their force that like push them or pull them apart. Maybe for the more mathematical audience, like those at IF, you're probably more familiar with the other example. Let's say if someone tried to ask me to explain why there are as many positive integers as integer, meaning both positive and negative number, that there are as many positive number as there are the whole real number, both positive and negative. I mean, if you were asked me to explain that, I cannot do it without talking about the concept of bijection or isomorphism. If again, this might sounds like a lot of scary words, but if you have mathematical training, you understand what I mean. If not, then that's okay. Now, come back to topics at hand, and I noticed that the organizer used one of this picture on the background. So people talk about the holographic principles, and they say something like a gravity theory is big quotation mark. It's a holographic image of some quantum field theory with no gravity. And there's a lot of articles written about this from popular science point of to the wide audience, like that you see. These are images that you find if you Google, like holographic principle. And it connected to, but then people also say that it resolves Hawking information paradox for black hole. It implies emergence of space-time and all other cool buzzwords. So I mean that's all good, but you might also ask, how or why, like as in the previous slide. I mean, a gravity theory is very different from other things that we have, and the one of them, for example, one of them on the other side, like this quantum field theory, there's no gravity, and so how in the universe could it become a gravitational theory? Like how come the world is a hologram? I mean, that doesn't look like there's any hologram in our world. That is one of the question that I would like to explain. And before we talk about like what does it mean or why or how is gravity theory is like a hologram of a quantum field theory, then I need to discuss this framework, like similar to explaining what electromagnetism is. What is the concept of fields in electromagnetism, or the concept of isomorphism and bijections. And this framework, where we agree upon whether things are true, this is a framework called duality. So I will tell you what it is. And this is a concept of a quantum field theory. So I need to tell you some basic about that. And then I will have to, more precisely, I want to emphasize on whether, if we say that a theory A and a theory B are two things that seemingly different are dual to one another, like what does it mean that we have to show? Then I will go through some of the examples, and hopefully by the end of it, we understand like more in which sense the universe is a hologram. The precise statement is that a theory of gravity is dual to a quantum field theory. And now we will know. We talk about what does the duality means. This is the most important part of this talk, that like there are things that we have to show to say that something are dual to one another. And this is a precise scientific claim. That's probably like science fiction sounding. This is a scientific research, and it's a scientific claim, and the claim need to be proven mathematically or require supporting evidence in order for us to believe that it is true. So let me say a few words about quantum field theory. So when we talk about a quantum theory, it means that if we had started with a classical system, it's described by the following Lagrangian. And consequently, it gives you the equation of motion. It's roughly F equal to ma. This is the fancy way of writing it. But the quantum system is it's described by different B's. It's not just a single object called the action or the Lagrangian, but it's the something called partition function, which is a sum of every possible path that connected, let's say, the event from point A to point B, like when you were born and until you die, instead of like the usual classical trajectory that we experience the quantum. Well, if the quantum world has a life, then you have to sum over possible event in your life, a possible trajectory, every possible choice that you make. The different way of extracting the observable quantities in quantum world, instead of maybe touching it in the classical world, then you have to perform like averaging sum over all the possible paths. Let's say like every possible choice in your life, or every possible path that the quantum particles can go. That was quantum physics. So what about quantum field? A quantum field is basically you replace the objects that maybe describe a position of a particle as a function of time to something called field, which is depends on both space and time. And you basically sum over all the path. And here path, it means like every possible configurations of this field in space and time and their evolution. For example, you can imagine like the quantum field that we most know about is the electromagnetic field. Like imagine like there's electromagnetic wave floating around us everywhere. They have different field configurations, like maybe different sine wave or something like this. And so what this sum over path mean that you sum over every possible configurations here and the evolutions. So maybe from this configuration evolve into this configuration, and then you repeat that to every configurations. And observable is again obtained by like averaging over all this path with this weight. It might be obvious to say here that this is a complicated process. For in some examples, we know how to do, like to perform this sum over all the path. In most cases, we don't know. So now we can start talking about duality. So now that you heard about quantum field theory and you are a master of quantum field, let's talk about duality. So suppose there is a quantum theory A and B, let's call it by this name, non-creative name, that they seems to be describing different things, and we say that they are dual if every possible observable and physical parameters in theory A can be mapped into a theory in B. So namely, there's a dictionary that translates one physical thing, every physical thing in A to every physical thing in B. So once that it happens, we say that these two theories are dual to one another. There is a baby example of this kind of thing, which we might have seen before in our study in undergrads. You may call it classical duality, but that nobody used this terminology really. For example, you can have a system of a spring and mass described by like the usual second order differential equations, describing the positions of the part of the mass attached to a spring. With spring constant K, with mass M, and all that. And you can have another system, very different one. It's composed of capacitor and the inductors, like the LC in the LC circuit of a first year undergrad textbook. And they describe by, well, the profile, how the current evolves in time, described by this equation. And you may notice that, okay, if I want to understand one of these systems, I can build, let's say I want to understand LC circuit, I can build a spring system, and I just translate the position into the current of the spring into the current, and I can take the spring constant over mass to be 1 over L and C, the inductance and the capacitance of the circuit. And I can just use one of them to study one another. It doesn't mean that there are every spring and mass system for every LC circuit that you can build in the world, but these two are equivalent mathematically. Needless to say that this is a bit boring, although the caption here already keep it away. So let's talk about some more interesting example. So the first one is electromagnetic duality. We start with Maxwell theory of electric field, describing electric field and magnetic field in the presence of a charged particle, like electrically charged particle. There's a current charge density and a current density over here. And then these are the magnetic Gauss law and like Faraday induction law. So this is one of the system. And there's another one. So there's no magnetic charge in our world. Like magnetic always come in pair. They have you have both North Pole and South Pole come in pair. There's no like single North Pole or what people call monopole, magnetic monopole. So, but if it exists, it would describe by this equation where instead of electric flux come out of some charge particle, there's a magnetic flux coming out of like magnetic monopole. And similarly, the induction law change slightly. You notice that I can just simply change the variables in similar to the spring mass system and the LC circuit. Just replace E to B, B to minus E, and the charge particle per unit, where E and G are the unit electric and magnetic charge respectively. You can just simply rename it, and then you're done. If you want to understand the theory with magnetic monopole, then you just use this duality, saying that, oh, okay, then I just use, just go to the electric picture and just change the variable, and then I get the answer of how, maybe two monopole interact with one another. So doesn't sound so exciting at the moment, but there's more to it when we talk about the quantum origin of this theory. Because electromagnetic electromagnetic field is a quantum field, and electron is a quantum object. Oops. Okay. So remember that we have to sum over all the path, and sorry, I think I skipped one slide. Yes. So in quantum system, there is a kind of like a magical relation that tells you that the products of electric charge and the unit electric charge, the smallest possible unit electric charge that you can have in the universe, and the smallest unit of the magnetic charge you can have in the universe if it exists, then the product of them must be equal to 2 pi in some unit where h bar equal to 1, c equal to 1, the speed of light equal to 1. So this relation exists, and you can show that it has to be in order for the theory to make sense. Since like this is out there since the work of Dirac, maybe almost 100 years ago. So in this case, instead of just like a mapping the ratio of the electric charge of the electric particle per electric charge per the small unit of electric charge, then you actually can map the smallest unit of electric charge into like smallest unit of magnetic charge. So the correspondence was a bit stronger, and every physical parameter, electric magnetic field, charged particles, the smallest unit of electric charge get translated into different picture. There's a nice review by Figueroa Ofaru called Electromagnetic Duality for Children. It's not really must be very intelligent children, but like it explains these things pretty well from many different perspectives. Okay. And then there's more to it since we talk about quantum theory. We essentially have to sum over all the possible paths and configurations. And this relations, electric charge times magnetic charge equal to 2 pi times integer. This is extremely powerful. For example, we can imagine the following thing where there's some photon, some light particle come in, and it pair create into a positron and electron, for example, if that happens. But there could be a different process where, like, as the electron, let's say, propagate, described by this line, and collide with the photon and go out, it could be that there's a virtual pair creations of a photon coming in and out, or the photon could split into electron-positron pair and they annihilate in between. So there's this virtual process. There's a lot of them, and you can classify it. But you see the more, and this picture getting more and more complicated. But luckily for a small value of unit electric charge is parameter E, then there's basically only this full process that will contribute, and then there will be the higher order term, the more complicated virtual process take place. And in general, for the large value of E square, where we cannot think of these like process as it's like small parameter expansion, then this thing become very complicated. But somehow, like, electromagnetic duality tells you that, like, if you want to compute the physical process, like, instead of a computing contribution from a lot of these virtual process, it turns into a process where only a few magnetic monopole pair, like, let's say, instead of just particle and electric and electrically charged particle pair creation happening here, it become like a magnetically charged particle, for example, and there's a few process of that happen. So this is when people say that, then there would be that for the electric theory with strong interaction, meaning that large parameter E, where you have to take into account a lot of these virtual process creations, or like what we as a quantum field theory is called loops. When there's a lot of loops with large electric flux, it's turned into a weakly couple of magnetic theory. So electric charge turned into a magnetically charged particle with a small loops. And these are two very different objects, and somehow these are equivalent. So well, I shouldn't say somehow too much, because you can actually do the implicit computations and then you match them, the physical quantity from both pictures with this value E equal to 2 pi over G. So this is a precise statement to say that, well, okay, we can argue that it exists from the previous classical picture, and you can also do the actual physical computations, and these two things match one another. Even though it seems to constitute like two different kind of particle, one picture contain only electric charge, the other one contain a magnetically charged. There are more interesting examples, like this is something called a sine Gordon model, which also exists in study of integrability and study of crystal dislocation. So imagine, let's say, a mass on a spring, and there's lots of them on the chain. Where we say that, okay, let's write some fields, which is basically roughly this displacement divided by the total distance of the chain of a system. We can write the Lagrangian of this system in the following form, where this is just like basically like some, well, like this is a unit mass of a like small region in the, well, like mass density of the spring, and this is like a spring constant density, and you integrate over the entire space. So you have these mass and spring particles take roughly the same form. We can try to complete them using slightly different model instead of changing this phi square term into something like a cosine, where if phi is small, then it's approximately turn into like this Lagrangian. So this system has this spring system has two kinds of solutions. One of them is just the normal oscillations, where these particles, by these like the wave of the oscillation of these spring particle of this spring, just like just shaking up, just shaking left and right, or if we plot the value of the field over the distance, and it would be like just this ripple, and as you change in time, it just like ripple up and down. The other one is called solitonic objects, which is the configuration where like there's some cluster or particle of a spring move here, move in this direction, the other one move there, and as the time progress, like this big slope here just move left and right. But it's not moving up and down. So these are two kind of oscillations that you can find in the system, and we can try to quantize it to make it a quantum field. There are two quantities that you can use to distinguish these two, which is the derivative in time of this field, derivative in space of this field. It's just something called, sometimes people call it like a number, the usual density and the widening density. Anyhow, then there is another system which is a system of fermion. It consists of a two anti-commuting number, meaning that if I switching these two number from left, instead of like A times B equal to B times A, it becomes A times B equal to minus B times A. So there are these kind of objects which we call fermions. And these fermions described by like the similar Lagrangian, slightly different. The point is that there are interaction between them, where basically two fermions can come into each other and then they scatter out. So this is the usual scattering process that is described by this classical action. And then you can also quantize this system. This is very different from the previous theory, obviously, because the previous one you get the boson, and the other one you have a fermion. So how in the universe they can actually match? But it turns out that the partition function of these two systems are identical, and then you can match every possible state in one quantum theory to another, and you can use that to match all the observable, and they all match. When the parameter beta in the previous picture of the spring and with some potential, this beta particles here turn into 1 plus g over pi. And I should emphasize on the appearance of 4 pi and pi here, that then these are like a precise number. If you want to match things precisely, then these are the exact value that you have to take, the exact relation that you have to take. And what interesting here is that this parameter beta over there, it kind of like control like this interaction or this like virtual process of the quantum field of the like quantum field that describes scalar system, and where G is the like basically tells you the interaction strength of the fermionic theory, but for two fermion come in and it go out. So the strongly coupled boson turn into the weakly coupled fermion, and the interesting thing is that these soliton configurations is mapped into a single fermion state. And one way to see this, one way to understand this is perhaps like from this picture, that if I crank up this parameter beta, then there will be, it turns out, and you can do the computations, that there are more and more of these solitonic objects that pop up, and when beta is very strong, then a lot of these solitonic is acting in the same fashion as the weakly interacting fermion. So this is kind of bizarre if you were to put it this way, that somehow the duality, even though they come from very different constitutions, all the observable match and every possible quantity that you can compute in one theory can be taken to one another. It's slightly more than just changing the name of the particles of the variables, like in the LC circuit example that we discussed earlier. So, and this brings us to the part that we want to understand, that I alluded at the beginning of the talk, like how the gravity is dual to a quantum field theory. And the statement here is that every possible observables in quantum gravity can be mapped into every observable in quantum field theory in the same manner as the duality that we discussed earlier. However, there are a few problems. First of all, the quantum gravity is very mysterious. We don't really know how to construct them. A quantum field theory, it's better understood, but it's still pretty hard. And even in the case where we can define quantum gravity, for example, in string theory, it's difficult to compute. In quantum field theory, the weakly coupled theory limit where a few virtual process happen, this is doable. But when a lot of virtual process happen, when the interaction is strong, then it's also getting pretty difficult, and we don't have a complete understanding of it. Also, in gravity theory, there's one clear-cut semi-classical limit, namely the classical gravity Einstein theory of relativity that we use and all in love. However, there are many quantum field theories that they can describe. There are quantum field describing many things, both exist in nature and whatnot, ranging from from the subatomic scale to like the tabletop condensed matter system. And there are various limits of them, but the classical limit where where the quantum field become classical, like classical electromagnetic field that we have around us these days and we use to communicate, it doesn't look like gravity at all. So it's a bit mysterious of how these two can possibly match. And there's a statement, area of research called ADS-CT correspondence, or the holographic principle. It has many names, but these things are what making this matching of observables in quantum gravity and quantum field theory precise. For example, the particular example that we understood the most is the quantum theory of gravity in string theory. It's called the type 2B string theory on some space called ADS5 times S5. To understand this, ADS5 is like it's kind of like a throat of some sort where you have it's kind of like an elephant trunk which ends somewhere when the trunk connected to the elephant. And the boundary of this space is some space called M4. It could be flat space, it could be sphere, it could be some other things. And as you go further in the throat, then the unit area of let's say each coordinate slice, as you go further inwards from red to blue, then it's getting bigger and bigger. And this space is the S5 part. It means that this is a string theory in a space where at every point in this ADS5 space-time, you attach a circle, a five-sphere at each and every point. 5 sphere means that it's a sphere in 5 dimensions. So this is a theory in 10-dimensional string theory, but we can say that, well, okay, this S5 is kind of small compared to the rest, and we can kind of throw it away. Maybe I shouldn't say it kind of too much, because we try to make things a bit precise here, but this is as precise as it can get, keeping the format. On the other hand, we want to match observable in this string theory, living in this weird space-time, into some weird theory living in 4-dimensional space, the same space as the boundary of ADS. But it doesn't live near the boundary. It's just something entirely different. Like here, there's a string. There's strings propagating around, and there are gravitons as a consequence of having strings. And this is some quantum field with no gravity. There's no 5 sphere attached to every point. And this is the sum theory with the specific field contents. It's not just one scalar fermion, but collections of them. This is called n equal to 4 SUN supersymmetric Young-Mills. The details here are not particularly important, but I hope to convey you that these two things are very, very different. However, not only holographic duality provide the connection between two related things, it's also related parameters in this theory in a precise way. And there are arguments that that help us guessing which parameter to match and what space to match to what quantum field theory, back in the 1997. And basically, but roughly there are two parameters in the string theory. So first of all, there's a size of the string, how big is a string compared to the size of the space. And then there's a string coupling, which tells you that if one were to have a string worldsheet, that it might be split it up. For example, maybe there'll be one string here, and it could and one string there, propagating it in time. They collide together and it go out. How often that this process will split into a different configuration, it's some version similar to the loop diagram in the quantum field theory we're talking about, but instead of point particle, we have a string. So these are two parameters in type 2B string. On the other hand, on this n equal to 4 SUN Young-Mills, these are names of things, but there are two parameters. One of them is the number of colors of the system. It just basically some sort of degree of freedom that you have, kind of tell you how much degree of freedom you have in the system. And then there's a coupling constant, basically, which tells you again how would these particles that you have in quantum field organize into these virtual pair creations. And the interesting thing is that in the limit where the classical gravity, where string theory turned into a classical gravity, namely when the string coupling is small, so there's no quantum corrections coming into it, and also the string is very small compared to the size of the space, so that we can just ignore that there are strings, that we just see a point and not the fine structure of the string. That in that limit, we can relate these parameters to parameters in a quantum field theory in a precise way. So that there's a 4 pi here, there's a power 4 to the 4 here, and these things are something that is just really difficult to guess. But there are arguments to show that it is supposed to be this way. And of course, but once you know these things, and then you try to say, okay, well, that this might be the case by some smart arguments, but how do we show that this is really true? Then what you would do is you find like some meaningful quantity in string theory, however you like, and then you have a compute. Then you want to match to relate or have a dictionary to relate this meaningful quantity in string theory, gravity, and I use these two terms synonymously, and to translate this thing into something, some observable, some computable observable quantities in quantum fields. You can also try to deform it away from a string theory ADS5 cross S5. So let's say change this space into something else, and it will corresponding to a deformation away from quantum field, like adding some additional terms in the quantum field Lagrangian, for example. And once everything is matched, then we say that this duality is proven. It is still not proven. So there's a lot of progress in the last 20 years or so that like try to develop a lot of these dictionaries and try to do explicit computation on things that we can do from both gravity side and quantum field theory side. And this list of the things that we managed to match is still growing. So that's basically it for what does it mean for the quantum field to be dual to gravity theory, and this is they related in this sense that every possible observable in quantum gravity, you have to be able to translate that into every observable in quantum field. And there are roughly three ways that people have been pushing these ideas of what kind of research topics that we're still doing these days. First of all, like we want to push the known conjecture, basically because there are arguments saying that these two should be equivalent, but there's no proof because we haven't matched observable. So let's try to match more quantities in a more precise manner. And this is not an easy thing. It's the computations are not the easiest one in string theory. Of course, also quantum field theory is also slightly difficult to compute a lot of things, especially when the interaction is strong and there's a lot of loops, these virtual process and loops that come into play. So new computational tools and technique, new mathematical structures are developed from both sides of the picture. Also, people try to conjecture new duality. For example, like if you have different quantum field theory, like maybe different structure than what I just mentioned, like what would that correspond? What would be the gravity theory that correspond to it? Or if your space in the gravity theory is not ADS5 times S5, but something else, then what would be the corresponding quantum field theory? So people conjecture these kind of things, and there are many clever arguments why something is true. But obviously, after proposing these kind of things, or even before that, one has to think about what would be the computations that provide the evidence of these new dualities. Namely, the more you can match from both sides, the more believable it would be. And another way of doing that people do the research these days also, it's kind of like a leap of faith, basically. So suppose the duality exists, then can we use the known properties of a generic quantum field theory to learn more about generic properties of quantum gravity, not necessarily from string theory. Also, it could be that can we use properties of gravity, known properties of gravity, to learn more about the quantum field theory that we're interested. Since a nice thing is that the classical gravity, as we seen earlier, the limit of classical gravity it doesn't turn into the classical limit of quantum field, but like some limit that corresponding to bunches of loops of a regime quantum field where you still need to add a lot of loop diagrams. It's not a classical theory, but you can map that to much more computable computation on gravity side. So these are like the last theme of the research, and there will be more. I'm not entirely sure how well we're doing with time. I think this is pretty much about it. So let me give a summary. So historically, holographic principle motivated by by arguments, and there may be ways of telling story to the general audience that tends to make it picturesque or like simplify explanation. This is understandable. This is because quantum gravity is just hard, and both conceptually and also computationally. So that's why we start with arguments and observations. However, at this stage in time, like the statement of holographic principle, and also this is a precise statement that quantum gravity is dual to a quantum field theory. And now we know that duality means. It means that you have to match every possible observables that you have in this quantum system to one another. I barely explained the holographic part of the story of how this name came from, or like how to do the computation precisely. So perhaps maybe next time, if one interested, and perhaps in a more serious format where there will be a lot more equations. But I hope at this point, then this gives you a better sense of how the universe is a hologram. Or thank you so much.
All right. Okay. Well, thank you very much for this very interesting talk. I mean, well, about the overview of this connecting between two different systems, right? The way that you use these two different systems, they connect through the dictionary, right here. And so I don't know whether I'm understand correctly or not. Is that what you mean by the dictionary is a set of somehow transformation of physical observable? Is that right? From one system to another system?
Plus yes, precisely. So
yeah.
Yes. So it means that if you, let's say you have some quantum system, you have as many operators, as many states, the way that Hilbert space is organized in some way, and there are lists of things that you can compute, and you can in one theory. And there's another one similar, again, Hilbert space, operators, things you can compute, and you match them like one by one. Let's say, okay, this go here, this go here, this go here, this go here. And so this is something called a dictionary. And if it does, then we say that these two theories are dual.
Okay. So, all right. So, well,
actually, that was a very good point. So let me add, like, maybe the two sides of the duality, as I hope I emphasize enough that it may look very different, and yet somehow you can match things to one another in a precise manner.
Mm-hmm. Yeah, that is very interesting point, because as you mentioned that these two systems they are very different, right, in nature, but you can use that kind of dictionary to translate some property on one system to another system, I believe. Mm-hmm. And I love your analogy, like spring system and the circuit that you used in the talk, actually to represent the duality that you.
I don't think nobody used the term duality, but I mean, if we accept the rules in quantum field theory, then okay, why not? It is a bit useless because you just change variables. It's much more interesting in quantum system where you need to add all these interactions of this virtual process, all this loop, and then it turns into something different. Classically, nothing like that happened, which is, I guess this is why nobody calls spring and LC circuit dual, but mathematically they're equivalent.
Yeah, but I think it's beautiful. It's make me easy to understand what you mean by duality with this very simple example. I think it's good. I think,
actually, and I hope I emphasize it. Let me emphasize it again. It doesn't mean that there is a mean that there is a LC circuit, but they're equivalent. or you
Yeah.
have a system of like spring or a spring chain, doesn't mean that there is a fermion somewhere. Or maybe there is, but I mean, it's just they are equivalent. You can map them to one another. It doesn't mean that it's there somewhere. And similarly, similar to this world universe as a hologram, I mean, it doesn't mean that there is a some screen somewhere that projecting holographic image of us. Could be, I don't know where, but this is just a statement that these two things are equivalent.
Well, that is a good question actually. Anyway, well, and then definitely you went further with another example between mapping between boson and fermion, which is actually another good example, right? I think that well, yeah, as you mentioned, that you can again. These two systems are totally different in nature, right? Boson and fermion, but somehow you have a dictionary to connect these two together. Yeah, I think that is another good example. And so, well, and you mentioned
actually, can I comment more on this part of the duality matching? So there are two input of this thing, the two sides of this thing. So first of all, then. At the beginning, it's difficult to say like what would be the observables, like how would you organize a Hilbert space and all that. So there will be some. Usually there will be some input. People might say, okay, well maybe this solitonic object is dual to a fermion, and but then you can use that and compute everything. So it's not just saying that I can draw I just make I make a list of 10 things. I make a list of 10 things and just draw the line between them. That's not true. So once you make the first matching, there will be consequence of that, which you can compute explicitly, and then you check that this is true. And the case of the fermion and boson, like in the Klein-Gordon and these fermion models, you can explicitly prove it. So this is a mathematical statement that these two are equivalent, and you can compute everything and you can match everything. This is something that usually doable in 1+1 dimension. In higher dimension, that is not true. In holographic duality, it's not proven. As I already said, it's not proven, but you have a lot of evidence. So which means that this list of things that you can match and like non-trivial check that you can match, that you can use to check, like from maybe not just drawing a line between them, like just starting from one and then go further as a consequence of that. That's the list is pretty long for the holographic duality in the case of n equal to 4 and their cousins.
I see. Well, okay.
It's less that there are less of them for the different kind of dualities, but this is basically the more you can match, the more confident you are that this duality actually works.
Yes, of course. Yes. Okay. And then you mentioned about ADS-CFT, right? But well, I don't know. Can you mention a little bit more about what is a CFT then?
Well, it's a special kind of quantum field theory.
Last
I think
idea about CFT.
I think that the short answer is I think it's how should I put this? I think the simple enough explanation. I think that the shortest one is that this is a special limit of quantum field. And what's special about it is that it's a system with the full Lorentz symmetry, like a boost, translation, rotations, combined with the scaling symmetry, and something called like a spatial conformal transformation. It's a bit of a weird thing, but it's roughly like the way that you map a circle into a line. Like you having a sphere somewhere, and you have a light, and you can project every point on the sphere into a plane.
Yeah.
So this is under this kind of transformation, that the partition function and the partition functions and like observables in this theory transform accordingly.
Okay, I see. All right, that I think that's simple enough for me. But
maybe if that's too mathematical, then another example of a quantum field theory, it's the critical system, but a system at phase transition at 0 temperature. So if there's phase transition, like a second order phase transition at 0 temperature. So like when the let's say when like I'm not sure whether this is the actual quantum field, but let's say the liquid ice gas ice transition or tricritical point of the water phase of the phase diagram of water, like this system is also scale invariant. It doesn't necessarily have a special the last transformations, but like usually we expect it to appear there in these kind of critical points.
Okay. Yeah. Okay. And so, and you give us a picture. I mean, the duality between like a ADS5 class S5 that actually represent the string theory in 10 dimension, right? I mean that is a superstring theory, right? Okay.
Yes. So the reason I mentioned I start with string theory is because like these are things where, well, we can say about quantum gravity in general, right? But there are many of them, the candidates of them.
Yeah, sure.
String theory is just the one that we know the most about how to compute things.
Okay.
And like there are arguments within string theory framework that tells you like what would be the dual of that gravity.
Okay.
So it's a framework in which we can do the precise computations. Doesn't mean that it not exists in other quantum field theory. Maybe this is just a property of gravity, classical gravity in general, or some other quantum gravity with no supersymmetry. But we don't know. I mean, we just probably true. But to actually say that there's duality, you need to compute.
Okay. Okay.
I mean, just argument is simply not enough. Right? Yeah.
Okay. So anyway, so I like the way the picture that you put in your slide. I mean the way that like the ADS space like a elephant trunk that you explain that type of thing. I think the way you draw a picture and but the thing is that because this theory it actually works on ADS space, right? Which is actually not usual space that we are living now, right? Is that going to be applied to this theory to make like matching or use this kind of dictionary between these two different theories? I don't know.
That is a very good point. So I was thinking about adding the slide about this, but then I noticed I ran out of slides and time. So again, so the reason why this duality between this complicated supersymmetric theory and like supersymmetric string theory that they found in the first place is it come within string theory framework, and it's rather simple solution in string theory. It doesn't mean that there's the only one. There's many solutions. But this is a simple one where you can actually compute and match. Now, if you ask about flat space, like a gravity with flat space, not in ADS. So let's say, maybe 4-dimensional flat space, like ours, or 4-dimensional expanding space, like ours again, kind of like ours. So is that supposed to be dual to some quantum field theory? Then, well, okay. So if somebody asks me this, then you ask me this. So then I would ask, okay, well, then how about you tell me what quantum field? Or if someone asks me, oh no, that doesn't have to be you. When people propose this kind of duality, then the natural question you would ask them is that, okay, then tell me what quantum field that you want to match it with. Okay, so if they don't know, then this is out of the question. Then okay, how am I even going to confirm that this is true? And then say, okay, well, then I say it's matched between this kind of weird quantum field theory. I don't know what it is. Maybe they explain. Maybe they write the action. Then I would ask, okay, then what did you compute on both sides? Does it match? Is it matched trivially? It is just like you match because you input, you say that they match. Are there any consequence of that where you can check that this is true? I mean, if that passes a lot of checks, then okay, then that sounds good. Then we keep making progress. And then the proposals of those things. This is still a pretty active area of research when people makes those claims. Certainly less evidence compared to the example I mentioned. Evidence means like non-trivial computation and checks.
Okay, I see. Okay. And well, you well, at the very end, you mentioned about holographic, but you don't. Yeah, definitely, you don't have time to explain that in detail. Yeah, and so what I understand is that this kind of duality or matching, or the way that you use dictionary, is that one system, it has a higher dimension, right, and at least one higher dimension than another one, right? Is that correct? Am I correct?
Yes, I
Is
think
that
so. That is true. So generally, this is So this is what. So again, that. So the example of n equal to 4 super young mules, for example, like this is not just 4-dimensional theory mapped with 5-dimensional gravity. It's the full string theory in 10 dimensions. So usually this is what this is the precise one, and then the one where we can actually do the computation and checks of this kind from string theory, because we can do the kind of quantum gravity computations. Now, if we just say, well, let's suppose in our universe or something resemble our universe where the internal space is S5 is shrink to a point, and then you just forget about it. And so you just have the ADS. And then this space is 5 dimensions. So it has some base with some, and then which is the same manifold as it has the same structure as the thing that the quantum field theory, but it has one extra dimension, this throat of the trunk of the left-hand direction. So it's one-dimensional higher, at least one-dimensional higher. So in that sense, we can say, well, yes, okay, so this 5-dimensional gravity is corresponding to 4-dimensional quantum field, or it could be 4-dimensional gravity corresponding to 3 means 2 plus 1-dimensional quantum fields. So this is like a simplified version. And there are some sectors of the, let's say, within the even classical gravity. We don't need to go supergravity or string theory. Just take classical gravity on the product space. Let's say AdS5 times S5. And then you can try to write out the equations and then decouple them from one another. So you can just there's some subset of computations where you can do on gravity that you just need to look at the AdS5 part, and then you have to find what would be the subsection of the sector of the theory. It's not all. I mean, just a part of it. Some observables that you can compute in quantum field that only care about AdS5 part. So these things do exist. So this is a simplified version of duality. But if you want to do the full-blown version, then I don't know how to do. I don't know how else one would avoid string theory.
Okay.
I mean, it doesn't mean that people haven't tried. That they do, and with degree of success. It's not as but again, this is about comparing a list of things you can accomplish within each framework. And there's a clear measure of how success your duality would be. I mean, the more you can match, then the more believable it is.
Okay.
I'm not sure that answers your question, but so the answer is yes. Guarantee is
Well, the reason why I'm asking this, because this kind of matching between two different systems which should have different dimension. Somehow you can use the word holographic, or the analogy of a holographic here, right?
Yes. So I think that's where the name came from. And it's I mean, it's good. It's very picturesque. It's very nice, and in some sense it contains some insight. But then again, we go back to previous comment. It doesn't mean that there's a screen somewhere or someone projecting a holographic image of this. I mean, maybe, I don't know, but it doesn't have to. I mean that's not the prediction of the theory. The predictions, the scientific claim is that they also will match.
Okay. So what I if I understand correctly, what you try to say is that we are not like a projection of something that actually live in the higher dimension, right? Is that what you're trying to say?
I don't know, and I mean this is like going in a like philosophical way, but that's
Okay.
not what this research subject is about.
Okay. Yeah. Okay. Okay. Yeah. Okay. That. My bad. Actually, I shouldn't ask that. All
Well,
right.
I think that I think that's a good point because a lot of popular science article they have this picture, actually the one behind you,
Yeah. Sure.
or these kind of things. So and like a lot of people in my community are guilty of communicating in this way, because I mean it took me like 40 minutes to barely explain the concept of duality in a very bad way. So it's just easier to say, oh, this is just like some light shining of some
Yeah.
boundary of
Yeah.
ADS go to inside and become like a hologram. That's much easier to say, and people kind of understand compared to going through like all this hassle of dualities. But
Okay. Okay.
the way we do the computations that we do are the one I just described, not
Okay.
holographic projections.
Yeah. Sure. 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 Definitely. Yes. Yeah. That give a more precise definition of what you mean by like duality or dictionary, that the word that you used. Yeah. I think that is better for understanding this kind of matching or duality between two different systems. Okay. I don't know. Is there any question from the online? Let me check. Let me check. Um, I don't see, and I don't see questions. But I see the the greeting words from someone to you.
Greetings.
Yeah. Like say hi. Okay. There is okay. There is comment here. Can you see the comment? เชื่อ
Yes,
หัวข้อ
yes.
นี้มากครับ Okay. Not the question,
You
but
can ask,
like a,
one can ask questions. I think again, there's no.
yeah.
I don't think I explain in the best way possible. But
Yeah, yeah.
you-
You can ask question in Thai, definitely. Yeah, please ask. Yeah, please. ถามได้เลยครับ ถ้าต้องการถามภาษาไทยพิมพ์ได้เลยครับ เดี๋ยวถามให้ so while we're waiting for a question, so I believe that actually I will stop put the survey form in the comment. If you have time, please complete this survey form for us. Then we can see all your comments, and we can use that to improve our activity next time. Okay. I still don't see a question yet. Let me check again.
Honestly, I was kind of hoping more that, to actually visit if personally, and we can have a discussions with more people.
Sure. Yeah.
But
Definitely. Yeah.
I mean
Yeah.
the time is a bit, well, these few years has been bad for that kind of activities.
Sure. For sure.
Hopefully,
But
we
I
will
hope.
get better soon.
Yeah. In second half of this year, when you are, as you mentioned, before we start live, right? You will come back. You will get back to UK, and then you come back here again in Thailand, and then you will start your work at.
Yes, my adult life.
Yeah, a new chapter of your life, I believe, at Chulalongkorn, right? Okay, and then definitely at that time, I would like to invite you here. Okay, can you read your the question? Oh, pretty long question actually.
Okay, I see. So I'm not sure about the second part of the questions about whether this support the theory. So I mean, if you match everything from quantum gravity, whatever it is, to a quantum field theory, Then once you do that, then there's a few implications. Then it means that, well, first of all, you solve the quantum field theory. Because I mean, to do that, you need to match everything. You need to know everything about that theory if you can. Then that would mean that you also have a theory of quantum gravity, a well-defined theory of quantum gravity, because you can just define it from the holographic dictionary, like from the quantum field that you start and you define a quantum gravity. So that would be like a working definitions of quantum gravity, not just claims and all that, but like by defining it. Suppose you're happy with definition of that quantum field that you can solve, but usually if you solve it, then you ought to have a good definition. So yeah, that it means you have a theory of quantum gravity that you can use it to compute things and derive predictions. And that would be the impact on quantum gravity, which unfortunately we don't have yet. There's a good evidence that it is due to quantum field theory, but again, there's no proof. It's even difficult to define what the quantum field theory is in a computable, mathematically precise manner. So that is already hard. There are rigorous definition of quantum field theory, but I don't know how to compute anything from it. The working definition that you see in textbook, it's not mathematically rigorous.
Okay.
And this is just quantum field, not even talking about quantum gravity. Then we can talk about quantum gravity as a string theory, and then you have to mathematically precisely define what it means by string theory. But then again, and since we talk about string theory and other quantum gravity, let's mention the following things. So it's not necessarily true that quantum gravity is equal to string theory. It's just the working one that we have right now that we can compute. So I see. Let me finish this question first, and then I answer the other one.
Yeah.
So then the question is whether quantum gravity is string theory. I'm not sure ADS-CFT is able to distinguish that, because so far what we can compute is we use the computability of string theory to make progress. There's slightly different approach, like using quantum information approach, definition of quantum field theory, and then use that to reconstruct what would be the gravity. So it's like you believe that duality exists beyond supersymmetric, beyond string theory. Just say, okay, I define quantum field theory through this from quantum information point of view, and I want to take that to gravity and define a new theory of quantum gravity. Would that agree with string theory? Probably yes. Maybe one of them may be subset of one another, but I don't know. And again, this is an open area of research. So can you repeat the previous questions?
Yeah. Joe, can you bring another question, please? No, not this one. I think, this one, yes.
How to separate one-to-one and duality. So usually when we say duality, we mean that a one-to-one mapping of one quantum field theory to another. And one-to-one mapping is usually a general concept, right? Like positive integers and positive and integers, like that kind of projection. So duality is a bit, it's like it basically one-to-one map with extra step that it used in the concept, at least in this vocabulary, it used in the concept of quantum field theory. And it as I say, it's not just drawing lines between two things. It's you make one line, and there will be consequence of that, which you can use to check and test the validity of your claim. It's a scientific research. Again, you need to be able to verify whether what you say is true or not.
Yeah. Okay. Any more questions?
These are all very good questions, by the way.
I think there's no more question. But let me ask you. Maybe ask your opinion or your comment about, because you mentioned about information right here.
Shouldn't have, but yeah, sure.
that well, actually, what do you think about the idea about emerging space-time? That actually, yeah, actually, I put this kind of fancy picture in my page, and then you come in and you put a comment, and then what do you think about this kind of direction research? Because it involves, of course, this string theory, definitely, right? Somehow, I don't know.
Okay, so there are a few things. There are a few things about like this whole program. So you can ask, then, well, suppose I have a quantum field theory. Let's say in 2 + 1 dimension, and somehow from that, I can use this like framework, this quantum field, to define the gravity in one higher dimension. So could it be that like, okay, so somehow you got one extra space-time dimension? This is very weird, right? So because like, where is this? Yeah, okay, this would be a good dictionary question. So what would be this extra dimension correspond in the quantum field theory? Like what would be the process of like falling into the trunk of the elephant in the quantum field theory? Well, like what do you have to do there to see that? And how would the quantum field encode this information? Or how would quantum field encode this extra dimension within itself, even with lower dimension? And then you can start asking more questions about, but what if my quantum theory has 0 dimension? Then you suddenly has extra dimension, right? So space-time is emerge in that sense. So that would be explanation of like how the how the space-time, how this emerging of space-time, the buzzword came in. Another one, the other thing is about quantum information. So there are ways in which quantum information theories define a quantum theory, and by extension, a quantum field theory. So in this way, there progress in which you can start thinking about, but then let me start from quantum field theory. I define like quantum information, blah blah, or quantities or properties in the quantum information language. How would that translate to the gravity side? Like what would be the, like, let's say monogamy of entanglement entropy, or like monotonicity, or these kind of things. Like how would that translate? How would that encode and capture by extra dimension? And what if you remove one of these properties? Like what would your new space-time would look like? So their progress making this direction. And many of them are non-trivial. So, I mean, I think this is a solid and interesting area of research. But yeah, so I don't know, like what precise is that? What was the more precise question that you want to ask?
Oh well, yeah, that is a good question, because I just want to know from your opinion, who are working on this kind of string theory, ADS-CFT corresponding, and then there is a buzzword about emerging space-time from this kind of area of research. Then the question is that is this solid idea, or this is just like I don't know. But you mentioned already this is kind of solid idea, right? Actually,
it seems like a solid idea, and it looks it seems highly non-trivial. But so I don't know what papers you have in mind, or what articles, or what aspect you're talking about. But I think maybe one lesson that not lesson. I'm not teaching anybody here, but maybe like one thing that one can that I hope that maybe when you read articles, or not you, just you in particular, that like when people read articles about these things, then you can ask, but what would be the non-trivial check that you can do? Okay, you claim that this is true. You claim that, let's say, information corresponding or entanglement corresponding to some emergent space-time. Okay, if you claim that this is true and probably true, what would be the check? How? Let's say if I screw up this entanglement property, what would happen to the space-time? Can you show that this is true? And is this like, or maybe dynamically, if system evolve like rapidly, like it has some quenching, it's oscillating. What would be the corresponding picture of the space-time that of the emerging space-time in that sense that you can predict? And moreover, does it satisfy? Is this emerging space-time that one used from starting from quantum field theory? Is that described by Einstein equation? So this is the last part is highly non-trivial. So this is talking about not just the emerging structure, but also the dynamical evolution of that system. Whether it would be like our gravity, the gravity that we know about.
Okay. All right. Okay. I think I think is okay. There is another question coming in here. Okay, can you read it? Yeah, definitely. I'm not sure if I understand correctly about So, could you repeat it again?
I'm not sure if I understand correctly that ADS5 in gravity sense at its boundary will give QFT of n equal to 4. Like you mean why is the maybe let me try to ask you. I'm not sure I understand the question. So you mean how do people know that ADS5 to S5 is corresponding to n equal to 4? Is that the is that the question?
If I understand correctly, that gravity sense. Oh. Yeah, I don't. Yeah. Let wait.
I in the meantime I can try to answer the question about why would how I mean, this is a very strange theory, very complicated theory. How do one know that these two are equivalent? I don't think I can explain it in 5 minutes. But imagine, maybe you can imagine this picture. So this is the argument in Modesina. Cannot find the elephant at the other section of elephant trunk. Oh, okay. So that. Well, again, this is a question. It's related to this overall theme that. So you can ask, okay, why would first of all, there's no QFT at the edge of this space. So this space is contain gravity. There's graviton everywhere, including at the boundary. Or if you believe in the ADS universe, we can just like run up and down, go to the boundary at the infinity, and then come back, maybe. And then there's nothing there. I mean, there's graviton and supersymmetric stuff and string there. There's no QFT. It's just that the mathematical structures of the space at the boundary of ADS is mapped to the properties to the space-time that the quantum field theory leaves. It doesn't mean that there's a quantum field everywhere, nor on the edge. Again, what would be the good analogy of this? Yeah, it just this is a corresponding. It's not like literally a quantum field there and it projected a light and turned into gravity. That this is not what this is about. It's a corresponding between observable in quantum gravity and observable in quantum field theory. It just so happened that the space-time of the quantum field theory that you use to define quantum field theory is a space-time at the edge, at the boundary of ADS5. I'm not sure that answered the question.
Yeah. Oh, I don't know. I believe that you do your best, I think.
And yeah. If you want to understand why it's ADS5 times S5 and n equal to 4, it's a complicated it's a complicated questions. I would suggest you read either like the books about this and that explain this thing pretty well, or the original 1997 papers. But the maybe the intuition is maybe the following. You can imagine having a proton and an electron, and then you want to ask what would be the scattering between these two things. And then so you can do two things. You can do first is you do the Feynman diagrams of maybe it exchanging virtual pair, electron proton exchanging virtual pair. Or the other one is that you replace the proton entirely, so the proton is gone, and it's replaced by some potential wave of electric potential, and electron just move in that background. And these two things are the better equivalent. So the arguments, Mondesina arguments for ADS-CFT is similar things, but instead of proton and electron, you replace that by strings and some object called d-branes. And when the potential, the electric potential that the d-branes create, it's not just a potential. It's also create like different space-time profile. Like once you take it away and replace it by gravitational solutions and like some other potentials, like supersymmetric potentials. So it is these similar kind of arguments that you can use to kind of guess like what would be the space-time and the quantum field theory that you use. I hope that makes sense. Although it wasn't asked, but in case one wonder how come one even possible come up with this. It's natural. It's basically the analog of this proton, replacing proton by potential in string theory.
Okay. All right. Okay. So, I think it's about time. I would like to thank our speaker again and everyone who stayed with us for this 1.5. Lovely speaking. We spent a lot talking about this very fancy topic. I like it very much, I think. And anyway, before we go and you go, please spend your time again to complete the survey form for us, and and see you again for this kind of activity, like if Colloquium number 9 next month, and stay tuned then. I think that's it for today. Bye bye. Thank you very much.
Yes, thank you. Thank you.
Okay.